Exponential functions. Exponential functions have an exponent that is a variable. Below is a formal definition, and it says it's a function of the form of f of x, capital C, a to the power of x. And then there are some things there that I think are important for us to understand. So a has to be a positive number. It says a cannot equal 1, and c cannot equal 0. So let's look at a couple of those things. So why can a not be equal to 1? So let's say see what happens if a is 1. So if I had a is 1, then I can fill in the 1 here. And 1 to any power is just 1. So then you just get c times 1, which is c. Well, that's a constant function. That's a constant function with whatever value c is. So for example, that could be rewritten then maybe as f of x. Let's look at that as a y then. So let's say maybe y equals 2. And we've seen just recently that y equals 2 is a horizontal line. So that would not be an exponential function anymore. So the next thing says, why can it not be less than 0? So let's see what happens if a is a negative 2. So then we would get this function, f of x is, now let's just assume that c is 1. Okay, so capital C here is 1, so you would get a negative 2 to the power of x. Well, if you look at that and you make a table for that, so at 0 it works great, so negative 2 to the power of 0, anything to the power of 0 is 1. At 1 you'd get a negative 2 to the first, which is just a negative 2. Then at 2 you would get a negative 2 squared, and the negatives are going to cancel each other, so that is 4. And then at 3 you would get a negative 2 cubed, and the negatives don't cancel each other. 2 of them do, but then the last one makes a negative again. And then you see you get sort of a zigzag pattern. So that's not a smooth curve, which is what an exponential function should be. So you can't have a negative base. A is considered the base. So the base A. You cannot have a negative base. And then the last one says why that c can't be 0 either. So if c were equal to 0, then we're going to end up pretty much in the same situation as on the top. And then you would get this. C, 0, and 0 times anything is 0, and that again, that's the constant function, y equals 0, also known as your x-axis. Okay, so there's some good reasons why the base has to be greater than 0, but it cannot equal 1, and a cannot be a negative value because of that then, and then c can't be 0. So that leaves us then with two types of functions, and the first one is right here. So there are two types of exponential functions. The first one is growth, and we'll see the second one here is decay. Okay, so exponential growth. Exponential growth occurs when a is larger than 1. For example, if I looked at f of x equals 2 to the power of x. So in this case, a is considered to be 2, the base is 2, clearly greater than 1. Right? What is the domain and what is the range? So the domain of the set is all real numbers. So the easier or a faster way to say that is, or write that is this way. And then the range would be the set of positive real numbers. So not including 0, that's why I have a round bracket, and then anything after that up to infinity. There are no x-intercepts, and the y-intercept is 1. So let's look at the picture there for that a little bit over here. So here's an exponential growth. So notice that there are no intercepts on the x-axis, and they actually mark this line y equals 0 with dots. Well, that means that there is an asymptote, right? So this is the asymptote. So exponential growth functions have an asymptote. If it's of this form, if it's just a base to a power of x, then the asymptote is always going to be the x-axis. And we can move the graph up or down by adding or subtracting, but notice here that it says exponential growth, a to the power of x only. Let's see, what else do we have? So the y-intercept is 1, so that one is over here. This is your y-intercept. And then just talked about the fact that the x-axis is the horizontal asymptote, and then it says if a is larger than 1, so if it is a positive number larger than 1, then it's an increasing function, and increasing in exponentials is called a growth, and we can ignore that, and it's 1 to 1. Okay, we will see what that means a little bit later in the year. Okay, then the next part here says 5. It says the graph of f contains the point 0, 1, right here, and then 1a and a negative 1, 1 over a. So let's look at what that means in this case again. So keep in mind that a is equal to 2, and we're looking then at f of x is 2 to the power of x. Okay, so exponential functions in principle can be graphed with 3 points. Now they don't always have to be negative 1, 0, and 1, because we can transform the curve. We can shift it up, down, left, and right. But you can still do it with 2 points, or 3 points. So anything to the power of 0 is equal to 1. So I call this 0, 1, that's sort of the anchor point for an exponential. Okay, that would be like the vertex for a quadratic. And that's an important point to find. So 0, 1 is indeed on our graph. So keep in mind that we are also trying to confirm this part. So 0, 1 is on the graph. So at 1 we should get a. So a is 2, so at 1 I should get 2. And that is because 2 to the power of 1 is 2. So that did work. So we did get 1a over here. And then on this one, the last one, if we do 2 to the power of a negative 1, keep in mind that that means you have to flip this, right? So this was 2 over 1. This then becomes 1 over 2 to the first, which is a half. So that does mean that at a negative 1 we get 1 over and a is 2. So that's what these 3 points mean. But keep in mind that this does depend on the value of the base. So a, again, it's your base. So when the base changes, so if a was equal to 4, then these values, 0, 1 would work because 4 to the power, so that would, if a is 4, sorry, we have 4 to the power of x. So 0, 4 to the power of 0 is 1, but then these would change. So at 1 you would get 4 to the first, you would get 1, 4, and at a negative 1 you would get 1 over 4. So that's a little different than a half, and the half that we got here and the 2 that we get here. So it depends on the base. Okay? Alright. So the next one then that we can have is we can have decay functions. Oh, sorry, the last one here is the graph of f is smooth and continuous. So it's a smooth and continuous line, which is why we can't have a base that is negative. So we can go through decay a little bit faster. So decay happens when a is between 0 and 1. For example, if I say that a is 1/3, then this would be f of x is equal to a base of 1/3 to the exponent of x. The domain and range would still be the same. The domain is still all real numbers, so you can put any x you want. The range, you get any values between 0 and infinity. But now it's flip-flopped. You reach infinity on the negative x side, and we get close to 0 on the positive x side. So this is still an asymptote. Okay, just like with growth, we still have an asymptote here on the x-axis. We get that over here. No x-intercepts, the y-intercept is 1. That's because anything to the power of 0 is 1. And we still get the points 0, 1, 1a, and a negative 1, 1 over a. But I do want you to look at that for just a second over here. So if a was 1/3, and then we're looking at 1/3 to the power of x. So now, again, we're going to use the 3 values for x that we used previously. So at 0, so that's the easy point. Again, this is the anchor. 1/3 to the power of 0. Anything to the power of 0 is 1. So 0, 1 is still on there. If you use 1, you just get the 1/3. Okay, and that indeed is 1. And then we get a over here because a is 1/3. On this one, when you use the negative 1, so the negative 1 makes that fraction flip, right? So it becomes 3 over 1 to the first. And then that's where you get your 3. So this is why it's a decay version, is because on the negative side, you get large numbers. And then it goes down, smooth and continuous, just like the other one. Okay, let's look at a couple of graphs. So here's an example. F of x is 3 to the power of x, so a is equal to 3. That means that this is a growth function, right? That also means that we have a horizontal asymptote. So there is a horizontal asymptote at y equals 0. So I'm going to mark that right now. And then we already know that the domain is all real numbers and the range goes from 0 to infinity. Because it's a growth, we should have small numbers on the negative side and large numbers on the positive side. And then if you want to, you could use transformations, but they get a little tricky with this, so it's often good to make a little table, keeping in mind that you want to anchor this. So this is my anchor point, right, at 0. So at x being worth 0, well, x in this case is just x, so I want the exponent actually to be equal to 0. So in this case that's just at 0. So at 0 you get 1. 3 to the first is 3, and 3 to the negative first is 1 over 3. So we get the value sort of that we thought we would, or sorry, we get the pattern that we thought we would, which is positive, large positive numbers on the positive x side, and approaching the asymptote on the negative side. So that's it, smooth and continuous. Same thing over here. Again, it's an exponential function, so you know that the domain is all real numbers. You know that the range is going to go from 0 to infinity because it's just it's an a to the x, so we're not doing anything else to it. In this case, because a is a half, so if the base is a half, it's a decay function. Okay, no transformations, so we know that y equals 0 is still the horizontal asymptote. And then if you plug this into a table, you could use a -1, 0, and 1. Again, this is your anchor. This is where your exponent is worth 0. Your exponent is equal to 0, which in this case is just x is 0. So plugging it in at 0 you should get 1, a half to the power of 0, a half to the power of 1 is a half, and a half to the power of a -1 means you need to flip this, so that's where you get your 2. So it works on this one as well. We get the larger numbers here, 0, 1, a half. Make sure that you keep this as a smooth continuous graph. We're approaching our asymptote, which I forgot to mark, on the right side now when x is positive, and that's it. Okay, so that's what everything looks like if you have very straightforward exponential functions. Let's look at a more difficult example. So what about this? Well, this just has, it has a bunch of transformations. For example, this is a transformation, the x plus 2 is a transformation, and the -5 is a transformation. Okay? The one that you need to be worried about the most is the fact that this x plus 2 shifts our anchor. Okay? So let's go through this sort of the same way other than that, and we'll see what I mean with that. So a here is 3, so this is a growth function. Okay? If I look at the overall function here, okay, this -5 over here, we just saw that on the hyperbolics, so that means y is a -5 is your new horizontal asymptote. Okay, we did that with the hyperbolics as well. The x plus 2 part over here, okay, this is going to produce my anchor, so and what I mean with that, the anchor is going to occur where x plus 2 is equal to 0. So that ends up happening at x is a -2. And why do you want to find this? Well, when you make a table for this, you will want the -2 to be part of that. You sort of want that to be in the middle. So this used to be my 0. So I'm basically using transformations here, although I am going to go back to my table because it's just a little more complicated here and it's a little harder to see what happens, and part of that is, in this case, the 2 here really messes things up a little bit more. But if you use the -2 and you do a -2 plus 2 over here, this is what I mean with your anchor. You get an exponent of 0 at this point, so 3 to the power of 0, and that is just 1, so we get 2 times 1, which is 2 minus 5, so we get a -3. So then you will want to see, well, what happens at a -1? So this would be 1 above it, right? So the -1 plus 2, and the -1 plus 2 here gives an exponent of 1, so that is just 2 times 3 to the first. Well, that's 6, and 6 minus 5 is equal to 1. And then at a -3, we should get our fractions. Because keep in mind, it's a growth. So on one side, on the positive side, we should get large numbers, right? And on the negative side, we should get our fractions. So if you do a -3, sorry, still stuck on the -1 there. If you do a -3 plus 2 minus 5, you get 2 times 3 to the negative first minus 5. And there you see you get your fraction. So 2 times 1 over 3, so that is 2/3 minus 5. That's like doing 5 minus 2/3, which is 4 1/3, but then we have a negative. Okay, well, since we're so close to 0, we might as well figure out what happens at 0 over here. So what happens at 0 now? So because you're doing 0 plus 2, you do not get an exponent of 0 here. We actually get an exponent of 2. And that gives you 9 here. 2 times 9 is 18 minus 5 is 13. And you can see how quickly this thing is off the grid. Okay, I think we go up to 12 here, but at 0 I'm already at 13, so I can't even graph it. Okay, and this is why I said it's so important to find your anchor. Okay, which we found here. And then you do 1 point here and 1 point there, knowing that it's a growth, so when I move larger numbers I should get positive values that are whole numbers. And when I go towards the negative side, or smaller numbers, to the left of the anchor, I should get my fractions. So everything here works, the way that I did earlier, but like I said, this is a more complicated example. So 1, 2, 3, 4, 5. So I'm trying to mark my asymptote. Then at a negative 1 I get 1. So that's a whole number point that's easy to graph. At a negative 2 you get a negative 3. So that was my anchor. And then at a negative 3 you get a negative 4 1/3. So negative 4 1/3 is just a little bit below it, right? And then after that we already know that we can't even graph the next one because it's off the grid. And then over here we make it approach 0. And then over here it maybe looks a little bit like an asymptote, but we know it's not because we didn't mark it. Okay? So that's a more complicated example. So in general, how would I graph an exponential function? Well, I would see determine if it is a growth or a decay function, because that helps me figure out where do I get my whole numbers, to the right or to the left of the anchor. After that, you should find your horizontal asymptote. Okay, and it's usually, it's here, it's given in the function. It's the transformation or shift up or down. And then the third part is you make a table around your anchor. With the anchor being the part when is, your anchor is going to answer this question. When is the exponent, the whole exponent, equal to 0? And that in an essence, actually it uses transformations. Okay, thank you.